Swayam Prabha. Digital India. Educated India.
Hello everyone. So, let us continue our discussion on the choice of pressure index N for stable operation of solid propellant rocket. We had begun our discussion by considering one N burning rocket, and there we discussed that how the mass generation and mass leaving the nozzle is going to be related, because we have seen that mass generation is going to be coming from the regression of the propellant. So, we can relate the mass generation with the linear regression rate R, and then we can use the burn rate law R equal to A p to the power n, and we have incorporated that in the equation. And for steady state operation, we have said that mass generation rate is going to be equal to the mass leaving the nozzle, leaving the nozzle, and doing so we have obtained a equation for equilibrium pressure, and we have said that if the value of n is close to unity, there is a little change in the parameters, for example, like throat area, burning surface area, propellant density. The value of A is going to make a huge change in the equilibrium pressure. On the other hand, if there is a small value of n, the change in these parameters will not make any significant change in the equilibrium pressure. So, let us see what we have written earlier. Like we have written that mass generation rate can be written as SB, which is the burning surface area, into R into rho p, and that we have written in terms of burn rate law, which is like in place of R we have written A p to the power n into rho p, and for mass leaving the nozzle we have written P c A t by, so here P c A t by C star, and equating these two we get the steady state or equilibrium pressure as rho p into A into C star into S b by A t whole to the power 1 by 1 minus n. And here we have said if n is near to unity, little change in these parameters will make a huge change in the equilibrium pressure, whereas if n is very small than 1, then there is no significant change in the equilibrium pressure. Okay. Now, we have also said that while considering these, we did not consider the change in the volume of the gas because of the regression of the propellant. Now, if we say that if due to the regression of the propellant, the volume of the gas is going to change. So, let us say using the ideal gas equation, mass of the gas we can relate with the volume as P v by R t, where V is the volume of the gas in the chamber, R is the specific gas constant, R means here R equal to universal gas constant by molecular weight, T is the gas temperature. Now, if we want to write this with the equations what we earlier had, that we had the dm dt equal to m dot g minus m dot n, or we had written in terms of like S b into A p to the power n into rho p minus P A t by C star. Now, we can write this by replacing m as P v by R t, that is equal to S b into A into P to the power n into rho p minus P A t by C star. We may use P c here Pc, or we can leave it like this. Let us not use it because it will be easier for us to write. So, we just simply said P here, P is actually the chamber pressure. Now, let us look at this derivative here d dt of Pv by RT. What we can write here is, since the temperature of the gas does not vary much, we can actually take the temperature outside of the bracket, R is also constant. So, we can have this derivative in the form of like dP dt plus P by RT dV dt. Now, what can we say about the dV dt? We can say dV dt is the change in the rate of change of volume dV dt, which we can easily relate with the change in this burning surface area into linear regression, because the volume rate, the change of volume rate is depending on how the regression is taking place. So, if this is my regressing surface, the volume is changing because of the regression, you know. So, it is coming to another this place, this place. So, we can relate that simply with the SB into R, because length is changing. So, we can just simply say that SB into R. And what about this P by RT? P by RT you can simply say it is the gas density. So, P by RT will be the rho, which is like the density of the gas. This is basically the product gas. So, now if we write the equation here, we want this equation to be written in the form of like the pressure change. So, let us say we just write this part, or we can just replace the whole thing there in this equation. Let us say this is equation 1, this is equation 2, this is equation 3. So, let us try to write in the equation 2 in terms of this. So, what we can write, V by RT dP dt plus this is becoming rho now, rho, we can say the gas density as rho g. So, rho g into SB into R, SB R means R is basically A P to the power n, that is going to be equal to this part, which is SB into A into P to the power n rho p minus P AT by C star. Now, for steady state condition we can say dP dt equal to 0. So, this equation 4, from here we can write that we can keep this density of propellant and density of gas one side. So, if you do that, it will come as SB into A P to the power n into rho p minus rho g, okay. That is going to be equal to P AT by C star. So, the equilibrium pressure equation will become A into C star into rho p minus rho g into SB by AT, this whole to the power 1 by 1 minus n. So, the difference between the previous equation and this equation is that earlier since we did not consider the change in the gas volume, it was only the propellant density, but now we have seen that this part is modified to rho p minus rho g. But one thing we can notice here is that rho p is actually very larger than rho g, because rho g is simply the gas density, rho p is like the propellant density. So, it is like a huge value compared to the rho g. So, therefore, even if you neglect this one, it is not going to make any much difference. In that sense, the equations we had earlier, it is equally can be useful. So, what we earlier got, P eq was equal to A C star into rho p into S b by A t to the power 1 by 1 minus n. That was our equation by simply equating m dot g and m dot n. Here there is a small change that rho p is becoming now rho p minus rho g. So, for a more accurate analysis we can use that. Now, why we are doing this exercise? We want to see that what is the typical values of n supposed to be in order to have like stable operation of the rocket. So, what we can do is we can actually try to plot the m dot g, which is in terms of like S b a p to the power n into rho p, and m dot n, which is mass leaving the nozzle C star. We want to just plot this as a function of pressure, and we want to see that for what values of n is greater than 1 or n is less than 1, we can get the stable operation. So, if we just plot them, let us say we plot this for n greater than 1. So, the mass leaving the nozzle is straightway is going to relate to the pressure linearly. So, this is m dot n, which is simply P c A t by C star. So, this plot is for m dot versus pressure. For n greater than 1, the mass generation curve will look like this. So, this is m dot g, which is S b into A p to the power n into rho p. So, the intersecting point will tell us the equilibrium pressure as per our equation also, that once we are equating the m dot g and m dot n, we are going to get the equilibrium pressure. So, this is for n greater than 1. Now, same thing we can plot it for n less than 1. This is straightway m dot n. For m dot g, it will come like this. So, this is the intersecting point which will give us the equilibrium pressure. Now, what exactly happening here is that if you will try to understand that once n is greater than 1 and what n less than 1, what is exactly happening. In case of n greater than 1, if there is a small change in the small increase the pressure beyond the equilibrium pressure, let us say the pressure is slightly increased to some extent and it is beyond the equilibrium pressure, the rate of mass generation is exceeding the rate of mass leaving the nozzle. So, the pressure will tries to increase further, because your mass generation is less compared to the mass leaving the nozzle. So, this will increases the with pressure, and the pressure will continues to increase until the rocket burst. So, there is a situation is going to arise that pressure will keep on increasing until the rocket burst. Now, if you look at the other side of it, in case that there is a due to some momentary disturbances, there is a result in decrease in pressure below the equilibrium pressure. What is going to happen? Here you see the mass leaving the nozzle is higher than the mass generation rate. So, since the mass generation rate is lower, the pressure tries to fall, since mass leaving the nozzle is higher than the mass generation. So, this will keep on decreasing the pressure until the stable operation is not possible. So, it is going to extinguish finally. So, eventually for the value of n greater than 1, stable operation is not possible. Now, if you look at the cases for n less than 1, for n less than 1, if p is beyond p eq or p equilibrium, that will cause the m dot generation. So, let us say if we due to some momentary disturbances our p is beyond p equilibrium pressure. So, it will bring to a situation where m dot g is less than m dot n. This will cause the pressure to decrease and get back to the equilibrium pressure. Similarly, when there is a drop in pressure due to some momentary effect, and here our generation will be higher than the mass leaving the nozzle, that will cause the increase the pressure and it will come towards the equilibrium condition. So, what we just said, in both the cases, either if it goes beyond the equilibrium pressure or if it is going below the equilibrium pressure, in both the cases it will try to move to the equilibrium pressure. So, here the for n less than 1 stable operation of the rocket is possible. So, because of that, the choice of pressure index is such that it is supposed to be less than n, and we have already discussed also that for double base propellant the value of n is in the range of like 0.5 to 0.6, and few cases it is even higher than that. In case of composite propellant, we have seen that it is in the order of like 0.3 to 0.5 or so, but of course they are less than 1 for stable operation of rocket. Okay. So, I think with that we pretty much understood the concept of mechanism of different type of propellants burning. We have related the choice of pressure index n, how it is decided for stable operation of the rocket. Now, we want to close this module by solving some example problems related to the burning rate, that we want to calculate some of the performance parameters when the burn rate law is given, so that we can typically understand that the concept of burn rate, how we can actually calculate the values of mass flow rate through the mass generation rate and how the mass leaving the nozzle. So, we can relate to that burn rate equation and we can actually get the data from there. One more thing I should try to tell here is that sometime the burn rate law is expressed in terms of some reference pressure, that R equal to A P by P reference to the power n, because you say one thing we should remember that the unit of R or the burn rate, it is basically the length per time unit, and in most occasion it is expressed in terms of like millimeter per second or centimeter per second. Now, if you look at the unit of A, it is like R divided by P to the power n. So, it is kind of a very arbitrary, awkward unit. So, in order to relate this unit of A with the unit of R, P is non-dimensionalized by dividing it with the reference pressure, and the reference pressure value is taken as 7 MPa or 70 atmosphere. And in that case, the value of R at 7 MPa is denoted as A70, okay, and the unit of A is of course is going to be unit of R. So, this is like this 7 MPa pressure or the 70 atmosphere pressure is kind of near to the operating pressure of the high pressure solid rocket. So, that is why this is adopted in practice. Now, in some problem maybe if the value of A70 is given, that inherently mean that we are talking about that the reference pressure is given as 7 MPa. Okay. So, I will try to show you one example problems relating to A70 as well. Okay. So, let us try to solve one or two example problems, so that we can close this module with greater confidence. Okay. Let us look at the tutorial problems. So, in this tutorial problem, what is saying is a double base solid propellant rocket is employed in a missile application. Following data are given. It is an N burning solid rocket. So, N burning means we can immediately we should have the picture in our mind that it is like the burning surface area is not changing, it is a neutral type of burning. So, it is a N burning rocket means it is burning like this, surface area regressing like this. So, the surface area is not changing. So, it is a neutral type of burning. Then it is saying it needs to provide, it is given the throat diameter as 30 mm. So, immediately if you wish you can actually calculate the the throat area, we should calculate the throat area. It needs to provide a constant thrust of 5000 Newton or 5 kilonewton. So, 5000 Newton. The propellant follows a burn rate law R equal to 0.004 p to the power 0.5, where p is given in Pascal and R is given in millimeter per second. You see these units are important. So, now you know that the value of p is in Pascal and R is in millimeter per second. So, this is typically R equal to A p to the power n. So, the value of A is given here and n is given here, okay. N is 0.5 and A is given as 0.004. Of course, it is millimeter per second, means we have to carefully use the unit, because pressure is in Pascal and R is in millimeter per second. So, we have to carefully use this. So, this is going to be very much, we have to make it consistent with the unit. Now, other values are given, like ISP is given as 1900 Newton second per kg, C star or the characteristic velocity is given as 1600 meter per second, rho p is given as 1540 kg per meter cube. Now, it is asking to find out the diameter of the propellant grain. So, if we know the SB, we can find out the diameter of the grain. If the rocket has to operate for 200 seconds, determine the length of the solid propellant grain. So, these are the two questions it is asking. So, in order to proceed that, we will immediately, as I said, we will calculate the throat area. So, you can do it yourself, but the values I got is like 0.0007 meters square. You are requested to check these values. Now, m dot, we can immediately write m dot as SB into R into rho p. How do you find the m dot? M dot we can relate with the thrust and the ISP data. So, thrust is given as 5000 Newton, ISP is given as 1900. So, if you do this, we can find the value of m dot, which is coming around 2.63 kg per second. Now, we can simply write our equation, we had m dot equal to P c A t by C star. C star is given here, A t we have calculated. So, from here we can easily find out the pressure, and it is coming something around 5951909 Pascal. So, you can use this equation of burn rate R equal to A p to the power n. Here it is 0.004 p to the power 0.5. So, you put the values here, you will end up getting the value of burn rate as 9.759 millimeter per second. Now, you bring this m dot equation, because it is asking about the diameter of the propellant grain. So, in order to get the diameter of the propellant grain, we have to find out the value of SB or the burning surface area. So, if you relate this m dot with the burning surface area SB into R into rho p, we can actually get the value of SB by dividing the m dot by R into rho p. R we just got. So, we put the value of 2.63. Now, 2.63 millimeter per second. So, we multiplied this 10 to the power -3, which is going to be in the meter per second. R is, sorry, this is wrong. This was our mass flow rate. Okay. Here the burn rate was given as 9.9759. Here we have to multiply with 10 to the power -3, and the density of the propellant is given as 1540 kg per meter cube. If you do that, you will get the value of SB, which is coming something around 0.175 meter square. Now, the diameter of the grain you can find out because you know the surface area. So, pi d square by 4 is going to be equal to your S b. So, this is your grain diameter. If you solve for it, I think it is coming as diameter of the grain is coming as 0.472 meter or 472 millimeter. Okay. So, this is the answer for question number 1. I would still suggest you please check the calculation once. Now, the second question was, it was asking that if the rocket has to operate for 200 seconds, determine the length of the solid propellant grain. So, if it is operating for 200 seconds, we know that for 200 seconds how much mass is required. We can say the mass will be like m dot into the time of firing. So, we can simply multiply that with the m dot into 200 seconds, that will come as 526 kg. You can get the volume of the propellant, which is like mass divided by the density. Density is 1540, that much meter cube. So, it will come as 0.341558 meter cube. So, the length of the grain how do you get the length of the grain? Length of the grain will be simply volume divided by the surface area of the grain. So, you can put the value of this 341,558 by 0.175. So, this will come as, here we have already calculated the surface area of the grain. So, we can get the value of the length of the grain is coming as 1.952 meter. So, that is for the answer of question number 2. So, this way if you just know how to relate the burning rate with pressure, with the burn rate law and the other parameters, and you know the relationship of our known performance parameters like thrust, the specific impulse, we can easily find out the values from the given values. So, this is one type of problems one can easily solve in this case. Now, second problem, I just wanted to bring you here the A70 thing, what we have just discussed, that A70 is the given at a reference pressure. So, in this question it is asking us to, let us see what it is saying. The problem statement goes by this, that an N burning rocket employs dB propellant density of this with a diameter of 125 millimeter and generates 205 Newton over 250 second with the characteristic velocity of 1350 meter per second and thrust coefficient of 1.2. Consider the following values for this propellant: n equal to 0.5, A70 is 3.2 millimeter per second. Determine the length of the grain, chamber pressure and throat diameter of the nozzle. So, I will just tell you how to do it, then I think you can try yourself and do this thing. So, immediately once it is given the diameter of the grain and it says the N burning, again it is a N burning rocket. So, we can immediately write the surface area as pi by 4, the diameter is given 0.125, that much meter square, since it was given as 125 meter 125 millimeter. So, I am converting that to meter. So, you can easily find out the value of this. What I got is like 0.0123 meter square. Then recall the burn rate law. We have R equal to A p to the power n. Here it is given as A70 is given. So, we should recall what we discussed already. So, we can write A is 3.2 millimeter per second. So, 3.2 into 10 to the power minus 3 into P as in Pascal. So, let us say P, we can convert that, P reference is 70 MPa, which is 7 into 10 to the power 6 to the power 0.5. So, now this R is going to be meter per second, since we have converted that to meter per second. So, the unit of R will become meter per second here. And remember, the value of A70 is given, means immediately we should use the equation by employing the reference pressure PREF, which is 70 atmosphere or 7 MPa, which is 7 into 10 to the power 6 Pascal. Specific impulse is given. No, specific impulse is not given. So, we can simply find out the specific impulse by multiplying the C stars into CF, because C star value is given 1350. So, we can use 1350 into the value of CF, which is 1.2, that will, the unit will be Newton second per kg. So, if you do this, it will come as 62 Newton second per kg. What will be the mass flow rate through the nozzle? Will be simply F by ISP. You put the value of F, which is 205 Newton given here, ISP you have just found out. So, 1620, this much kg per second. So, it will come as 1.1265 kg per second. What will be the mass of the propellant? Remember, it is firing for 215 second duration. So, we can simply write m dot into the firing duration T. So, it will come as 0.1265 into 215, this much of kg. So, that will come as 27.2 kg. So, what will be the volume of the propellant? You simply divide this mass by the density, which is 1900 kg per meter cube. So, this will be the density, which will come as 0.0143 meter cube. So, from here you can easily find out the length of the grain by dividing this volume by the surface area. So, V by SB. So, we put the volume 0.0143 meter cube by surface area was 0.0123. So, that much meter it will come, which is like 1.162 meter. So, that is the length of the grain. So, I think if you just do this carefully by applying the burn rate law equations, only thing you have to remember is the consistent unit. You have to use the unit very consistent, then only I think you can use it properly. So, you can get the value of the length of the grain. What about the chamber pressure? Again, the chamber pressure you can determine from the equation of the burn rate. So, first of all, we know the burn rate law R equal to given as A70 value was A value was given, which was like 3.2 into 10 to the power minus 3 into P by 7 into 10 to the power 6 to the power 0.5. Now, we do not know the value of R, but since we know the length of the grain and the operation duration of the grain, we can easily find out the value of R, which is the length of the grain divided by the operation the firing duration, which is 215 second. So, 1.162 meter by 215 second will give us the value of R, burn rate. So, now you put the value here, which is going to be like 5.4 into 10 to the power minus 3 is going to be equal to 3.2 into 10 to the power minus 3 into P by P reference, which is 7 into 10 to the power 6 to the power 0.5. You can easily find out the pressure here. Pressure will come as 19.95 into 10 to the power 6 Pascal, or it is like 19.95 or close to 20 megapascal. Okay. So, that way you can easily solve the problem if you know it properly. Now, it is asking about the throat area or throat diameter, I guess. Yeah, throat diameter of the nozzle. So, first of all you need to find out the throat area. Throat area you can easily find out from the thrust equation, which is like Cf equal to F equal to Cf into Pc into At. So, from here you can find out the value of At by dividing the thrust by Cf and pressure. I think you can get the value here, and from the At value you can easily find out the throat diameter. So, what we have learned here is that if you do it carefully, I think you can easily solve this type of problem step by step, just follow step by step. So, for the case of even if it is given for a reference pressure, if A70 value is given, we can apply the equation properly. Only thing you have to remember is that unit has to be consistent. Once you are talking about like P is in pressure and R is in millimeter per second. So, use the unit consistently, because Pascal means it is like Newton per meter square. So, we must need to use this unit in meter per second. So, that is why I multiply with 10 to the minus 3. So, while solving the problem, we must be sure about the unit. We have to use the consistent unit, then I think we should get the correct values. Otherwise, while solving the problem also, you may find some values which looks very different or kind of a odd, which cannot be possible in physically. Then definitely you can ask the question yourself, and you can also always look back that where I am doing the mistake. Okay. And that way you can actually find out the issues and you can correct it. So, I think with that we close the discussion of our this module of the entire module of combustion of solid propellants. So, with solving the problems, I think we pretty much now aware about how to employ the burn rate law equation R equal to A P to the power n for solving this type of problems. Okay. Now, I think we will start our next module, which is like combustion of metals, because that is also solid fuels. So, that will be starting the next lecture. Okay. Thank you.